Hi, how's it going? My name's Evan Angelle. I'm here to talk about the steam calorimeter with y'all. First question y'all probably have, what is a steam calorimeter? It's a pretty simple mechanical device. There's no moving parts in it. It's used in calculating the quality of steam in any any cycle, any power cycle you may have, the quality of the steam. Now what is steam quality? Steam quality is basically, it's a ratio, basically a percentage of the amount of vapor that a two-phase mixture has in it. Vapor to, as opposed to liquid. Or in this presentation, or in any book you might see or any class you take, it's represented as X mathematically. Now the goals of this presentation. First goal is to learn how to use the steam calorimeter. Learn its functions, learn just what its purpose is basically. And we're going to use measurements we take from that steam calorimeter to calculate the steam quality. Now why is this useful, you might ask? Well, it's useful in thermodynamics to fix states. I'm sure y'all remember from thermo the equation H equals HF plus X, whatever. I'm sure y'all remember that. It's very useful to have the steam quality, the actual value for it, to find all that, because it's relatively easy to find as opposed to the rest of the values. How can you apply it? You can apply it in analyzing power cycles. I'm sure from Dr. Gonthier's thermo class, y'all all remember the Rankine cycle, the reheat cycle, the cogen cycle, all of that. It's very useful in that class or in a real world application. Say you're working for working in a power plant. And for simplicity, I use a simple Rankine cycle. As you can see on this plot right here, at state 3, the working fluid is in the two-phase region of the temperature entropy diagram. And this is the ideal Rankine cycle. Your actual value will be more to the right of that, but you want to keep it somewhere in the two-phase region. And knowing the exact steam quality will help you in knowing exactly where your fluid's at and what kind of adjustments you might need to make in order to maximize the efficiency of your plant, which will better work output, lower costs, and make your boss happy. You'll make more money. Now the basic apparatus of the steam calorimeter, there's two major parts to it. There's a separating calorimeter and the throttling calorimeter. Basic processes of that is M1 right here represents the mass flow rate of the two-phase mixture coming in. First it comes into the separating calorimeter. The separating calorimeter does just what it sounds like it does. It separates the vapor from the liquid. The liquid comes out. M2 represents the liquid coming out. That goes into a drain, into a measuring pot. M3 represents the vapor that goes out into the throttling calorimeter. Now the separating calorimeter has, like you saw before, one outlet, one inlet. The liquid water falls out. The vapor water goes on to the throttling calorimeter, where it passes through. It's basically just a small orifice. It's a throttle, which can be described as an adiabatic pressure drop. Now this pressure drop, it brings the fluid into the superheated vapor state. And this, after that outlet, it goes into a condenser where it's condensed, it's cooled down into a liquid, and that falls into another measuring pot, where that pot represents the amount of vapor that was initially in your two-phase mixture. Other apparatus are pressure gauges, temperature gauges, and those two measuring pots. There's pressure and temperature gauges, a pressure and temperature gauge inside the separating calorimeter, and one directly after the throttling calorimeter. And you use those pressures and those temperatures, along with the volumes collected in the measuring pots, to fix your states, so you can, which is the information you're trying to find. Other apparatus are the condenser that I talked about. There's a sight glass inside the separating calorimeter, so you can actually see what's going on. And then there's valves that you use to just direct the fluid to where you want it to go. Analysis, you use the measurements that you take, the pressures, the temperatures, and the volumes, you put those into just some basic thermal equations, and that's where you use to fix your states to find out exactly what state your fluid is in, which is what you're really looking for. Predicted results, it depends on what your settings are, you know, how hot your fluid is, what the pressure is, and also the heat input time. You know, pressure rises, temperature rises, and the longer that it gets exposed to heat, that's going to make for a higher quality steam. An educated guess, it's probably going to be somewhere between 0.5 and 1. Uncertainties would go along the lines of your gauge qualities, how accurate they are. Unknown liquids that are initially in the calorimeter, that'll also throw your measurements off. And if there's any phase changes in the separator, that will also throw off your measurements. And this is a basic schematic of a calorimeter. Does anyone have any questions?